Thanks so much to Sylvan and CIG and the other organizers for this really important event. So the presentation I'll give today is, we'll continue this theme of exploring the role of fluids and pressure changes and how that influences fault slip behavior. I'm going to present work that was done by Yuyun Yang, Weicheng Zhu, and utilizing the code that Callie Allison originally developed, and possibly some very recent work that Sozawa has done. So the models that I'll show today are 2D anti-plane shear strike slip models. Fluid transport and pressure changes will be confined to a fault zone. I'll use rate and state friction, velocity weakening to velocity strengthening as usual. And the changes in fluid pressure feed back into the problem through the effect of stress. Here, the difference between the total normal stress confining the fault and the fluid pressure pushing back out. And I'll use rate and state friction. As I mentioned, fluid flow will be confined to a fault zone. I'll assume that it's uniform width. We'll feed fluids in from below. Thinking here would be that whatever reaction, like dehydration reactions or fluid sources that are producing fluids, they're happening below the region of interest. So below the seismogenic zone and below as you'll see, the slow slip region below that. Flow will be anything but steady despite feeding fluids in at a constant rate. And while the work is done for 2D anti-plane shear strike slip models, I do think that a lot of the processes that are identified have a lot of relevance to subduction zones as well. We're using a pore pressure diffusion equation. This comes from fluid mass conservation. The fluid is compressible, the pores are compressible, and we use Darcy's law. So the key quantities that you'll see are porosity, phi, beta, the sum of pore and fluid compressibility, K, the permeability, eta, the fluid viscosity. And this form here includes the weight of the fluid through that rho G term. And then we've included some inelastic porosity changes. They could be either due to creep compaction, a viscous porosity evolution mechanism, or plastic sort of fracturing and dilatancy type processes. It's really key when doing these problems to think about what's the structure of the fault zone. So is slip highly localized, and then in a low permeability region and low fluid storage region, and then a lot of the transport, at least along the fault, happens in a fault damage zone that has higher permeability, higher storage capacity, right? And if it's that latter picture, then the relevant fluid transport properties that we want here, at least when modeling over longer timescales, so this will break down over coseismic timescales, but the relevant properties are those of the damage zone. And so that's the perspective we'll take in this work. And that is assuming that there is time for pressure equilibration due to fault normal flow between the damage zone and the fault core where slip is localized. Overpressure, we'll talk about that. So fluid pressure greater than hydrostatic. And when you have overpressure, you have upward fluid flow. The term in brackets here, that's just the Darcy velocity. You can see it written here. And so just as a very simple model, think about steady state flow conditions with constant permeability and viscosity. You just integrate this with respect to Z, and you get a distribution of pressure. You get the hydrostatic rho GZ term, but then to sustain that upward flow, you have to work against that viscous resistance, and so you need a higher pressure gradient. So that's the overpressure. And the things that produce overpressure are the fluid production, and also I'll show compaction mechanisms. So I'm going to show two models, or at least one. We'll see if I have time for the second one. And they both explore different ways that permeability can evolve. And so we'll use a relation between permeability and porosity of this form. So typical power law form, Cassini-Kármán models would place that exponent around 3, and that's pretty consistent with many lab experiments. But there is this, and phi naught is just a reference porosity, but there's this parameter K naught, and that's where, even the same porous medium that has the same porosity, you could imagine different ways to connect that pore structure. If you have super straight channels, you're going to have very high permeability. If you have very tortuous fluid paths, you're going to have a low permeability, right? And so that all gets put into this, this K naught. And so then the question is, when you think about permeability evolution, is it because that pore structure is changing with relatively constant porosity, or is that structure fixed and then it's the porosity that's changing, right? And so that leads to two end-member cases. So the first model that I'll present, which has not yet been published, but we're sort of imminently about to submit it, I'll call it the compaction and dilatancy model. And so in this case, we'll have permeability evolution solely coming from porosity evolution. So only through changes in phi, and we'll do it with this K naught, this tortuosity or pore conductivity parameter fixed. This model will not only include elastic porosity changes, but also viscous and plastic ones. And then the second model, which has been mentioned already, and Luca, it looks like, is exploring some version of this, led to fault valving, and this has been published for a couple of years. In that case, we focus on the other end member where permeability evolution came from changes in tortuosity, or basically this K naught, we call it K star parameter in that paper, with phi fixed, the porosity fixed. Well, we did account for elastic changes in porosity. And there's no dilatancy or compaction in that study. So first I'll present this newer model that's yet unpublished. So we'll break down these different terms and think about the processes involved. So the elastic one is the most standard, so just changes in elastic porosity are proportional to pressure changes. There would, of course, be another term involving changes in total normal stress, but in this case, we'll assume that's fixed. And so there's just some coefficient here, proportionality coefficient that's defined to be the pore compressibility. You integrate that, and you'll see the usual dependence of porosity on effective stress. You pass it through a relation like this, and you get permeability depending on effective stress, right? And that's very, very widely seen in experiments. The viscous term here, this is the creep compaction term, and we utilize something that's similar, but I'll show you, it's similar to what Luca is using, but I'll touch, you'll see that the way compaction enters our model and the phenomena it produces is extremely different than in his model, and so I'll try to explain why. So we just use a thermally activated linear viscous flow law here, so we bring in some dependence on temperature. It's linear in effective stress. You could imagine there might be a power law, but we do it like this. And we view this as the reciprocal of that is the shear viscosity. So there are, if you go to the pore scale, and you think about, here I've drawn it as a spherical shaped pore, but you can imagine crack-like pores. So there's fluid pressure pushing out, there's a confining stress pushing in. And if this brown material, the rock matrix, is viscoelastic instead of just elastic, then anytime you have an imbalance of pressure and confining stress, you have deviatoric stresses within that matrix. And then you have viscous flow. And so it's that viscous flow of that matrix that compacts the pore, right? And then that squeezes the fluid, and unless the fluid can escape, then ultimately the pressure, it compacts until the pressure equilibrates with that confining stress. And so if you average over a lot of these pores, then you can think of this process as introducing an effective bulk viscosity. Of course, it's coming from shear or deviatoric straining, viscous straining in the matrix, right? And so there are relations between the effective bulk viscosity and the shear viscosity. For spherical pores, it's like this. For cracks, there's a weaker dependence on phi. There's great discussion of this in some of these classic papers, right? This is actually a very well-studied problem, but it sort of fell out, I think, of attention, and then now it's coming back in vogue, right? And so the compaction process is what will increase fluid pressure. We'll also include plastic porosity evolution. So this is dilatancy, and phi is drawn towards a maximum value. We use a Siegel and Rice type model inspired by Chris Marone's experiments. The only addition to it is we add in this elastic dependence on effective stress. You don't have to think about this as sliding on rough surfaces or super thin gouge zones, right? And you get down to slow slip depths, it's depending on what geologist you ask, right? It's either distributed or localized, right? It could be a lot of things. But you can think of this V over L as a strain rate over a critical strain. This is if shear is distributed over some finite width zone. So you can kind of map this parameter L, assuming some width of that shear zone, into a critical strain for evolution, right? And this might be relevant if you have distributed shear or if you're thinking about things happening in a damage zone. You put that into fluid mass conservation and go through the usual steps, and you get your pore pressure diffusion equation with these source terms. And so first I'll look at a steady state solution. So what is it that actually sets the distribution of fluid pressure with depth along faults? That's so fundamentally important to our modeling. The steady state here, we only get one if we balance dilatancy and compaction. And we'll set the fluid flux constant. We'll set it equal to a value that I think is reasonably appropriate for many faults. And then, of course, we have steady state sliding too. So we balance that. We get an expression for the porosity here. It depends on effective stress, and it also depends on a ratio of the porosity enhancement timescale. So that's coming from dilatancy. That's this L over V timescale. And then there's a compaction timescale, and that comes from the compaction model that I mentioned earlier. So we can plot those two timescales here. For simplicity, we just assumed a constant permeability enhancement distance L, so it has a constant timescale. But the compaction time decreases with depth. That's because temperature increases. Thermal activation of flow mechanisms lead to rapid compaction. So there's some nominal parameter value in red here, and then some ones that I may or may not have time to show, some variations in that. The distribution of porosity, things start compacting. Porosity is high near the surface, drops, and in fact, it levels off at asymptotes to some constant value independent of this rate prefactor. And we have a theory to some understanding now of why that is. But it stabilizes at a constant value. And similarly, porosity, because it's dependent on, permeability, because it's dependent on porosity, follows that same behavior, right? So we see permeability reduction, and then it goes to some constant low value. Now, what happens with pore pressure and effective stress? And I think maybe it's just easier to look at effective stress here. And so it increases linearly with depth. The pore pressure is hydrostatic near the surface. And then we start to get the onset of compaction, and that increases the fluid pressure, and eventually, at first it kind of starts tracking the fault normal stress, and then eventually compaction becomes more important than dilatancy, and this rolls over, and then the effective stress tends towards, if not zero, at least some very small value at depth. So what happens when you take this model and run cycle simulations? So we get really complex behaviors. This is log slip velocity in color versus time. This is the same thing for effective stress. So we do have large earthquakes that rupture the seismogenic zone, but then there's a lot of interesting complexity down here at the base of the seismogenic zone. And I'll just remark that the velocity weakening region goes down to about 17 kilometers depth. So this is all velocity weakening. We're going to zoom in because that's where we're going to see the interesting behavior. So these are slow slip events, and it's a fairly complex set of them. So here's what they look like plotted versus time, and on the right time step. There is a sense of the seismogenic zone up here being locked, low slip rates, out of steady state, and then the region below it, separated by the locking depth. Normally, you would think of this as experiencing fairly steady creep, but with these feedback mechanisms that we've introduced, it turns out this is unstable, and hence you get slow slip events. So the slow slip events, they're driven in combination, I think, due to combined effects of velocity weakening friction that causes the friction coefficient to drop, and then also compaction, which is causing the fluid pressure to increase. And the compaction here is happening over these interseismic timescales. It's a slow timescale process. And then there's a lot of stabilization. These never develop into actual earthquake ruptures where inertia becomes important for a couple of reasons. One is they're stabilized by dilatant suctions. And then also I think the compaction-driven pressurization nucleates them, helps them reach nucleation conditions earlier when the overall background stress is too low to help to sustain a self-sustaining, to support a self-sustaining rupture. If we zoom in even more, we can take a look at these three different depths here shown with the different colors just to get a sense of slip versus time. And so these slow slip events are locking in a couple centimeters of slip, and it's fairly consistent with what's seen in long-term slow slip events. And the periodicity, it's fairly complex, right? It's anything but periodic, but of order 1 year, months to a year. We can take a look at what's happening with compaction, right? You can move across here in time and see, the onset, before leading up to some initiation of some slow slip event, the fluid pressure is getting higher, right? It gets more red. So that's that compaction creating increase in pressure, weakening the fault, causing it to slip. And then you have a slow slip event like this one. Here you can see the fluid pressure drops. That's the dilatancy. Another way to look at this is just to plot a time series. So we'll do it here at 11.5 kilometers depth, right, where we see one slip, aseismic, slow slip event passing, and then another sharper one going here. You can see the porosity reducing in time. That's compaction. It's a long time scale process. That's increasing fluid pressure in black here. That's dropping frictional strength and causing slip rate to accelerate. When that happens, we get the porosity surges upwards, that's dilatancy, fluid pressure drops, that's dilatant, that's the dilatancy, right? And then that slows the slip velocity down. Something similar plays out here, but it's just a sharper event because the background conditions on the fault are different at that time. So that's the general mechanism here. I will note that the permeability and porosity changes in this model are very small. And therefore, this model predicts fairly steady upward fluid flow. The flow is key to creating that distribution of effective stress, but it's not a fault valving process. And the reason is basically what Luca explained. It depends on which is kind of relative importance of fluid compressibility and pore compressibility that controls the magnitude of these pressure changes. So let me jump ahead here. So I do want to point out that our model makes really, really different predictions about the role of compaction than Luca's model that he just presented. And I want to explain when you would set your model up in the way that he did versus the way that we did. So as he mentioned, right, the way that he deals with frictional sliding is by distributing it over some finite width shear zone and then using this viscoplastic rheology, right? And so the thinking is that it's this brown matrix material that's shearing and accommodating slip, right, integrated across that zone. And so then when the effective shear viscosity of that is dropped, right, you can see that viscosity dropping here in pink. It gets down to 10 to the 10 Pascal seconds. And it's that same shear viscosity that's controlling frictional shearing as controlling, and that same one is used in the compaction process, right? And then, of course, because this thing has very low shear viscosity, it compacts very quickly. That would be appropriate if kind of everything's happening in the same region and it's the compact, the matrix material that is shearing is the same material that's participating in compaction. This would not be appropriate if you have highly localized shear happening over here, right? And everything's frictional, but the compaction and dilatancy are happening in some, let's say, some damage zone, or at least some region around the fault where most of the fluid flow is happening. And that's the perspective that we've taken in our approach, and therefore the viscosity that we utilize in this compaction term is not reduced by many, many orders of magnitude during an earthquake. And so here I think we need both geologic guidance on what is the structure at, say, slow earthquake depths, how localized is shearing, what's the nature of porosity and compaction, and then we need experimental constraints, right, to to help think about, well, is it really appropriate to drop it to 10 to the 10 Pascal seconds or not, right? So lots of fun things for us to think about as a field. I want to touch just very briefly here before stopping on the second way that you can go about modeling this, a second in-member case. And this is the fault valving model. And so here we're thinking about permeability evolution by itself without inelastic porosity evolution. So there's no dilatancy, no compaction in this model. And the way you would envision this model as being appropriate is if the changes in permeability are dominated by changes in that pore connectivity or tortuosity. And there's several mechanisms now that would allow that. So if you had dissolution and precipitation reactions, so diffusive mass transport, and you dissolve the same volume, then reprecipitate it, right? You're not changing the overall porosity, but maybe that you've changed where you've placed that porosity, and you change the how interconnected that pathway is, or you can make it more or less tortuous. You could think about fine grain clays or something that are clogging and unclogging pore throats, right? And they're migrating around, right? Again, no changes overall in porosity, but you can change the permeability quite a lot. You could think about breakage and redistribution of mineral cements, quartz and calcite that have precipitated out, and then break them. And if you remove that and kind of move things around, but you do it in a way without a lot of dilatancy, again, you're changing that pore connectivity. So anyways, this model is relevant under those conditions. So they're the equations that Luca presented before. So here's the usual elastic one, and I mentioned the physical basis of that before. Different curves here for different K stars. That's sort of that tortuosity or pore connectivity parameter, and then we have it increase with slip and then decrease from healing and sealing processes. We're going to keep this time scale fixed for lack of, just to make it simple. Of course, I think it's undoubtedly thermally activated and hence should be a lot shorter time scale at depth. That model, just with that nonlinear dependence of effective stress of permeability on effective stress, gives you this Rice et al. Effective stress profile. Pressure starts tracking the fault normal stress gradient. But when you add all these dynamics, you get interesting behavior, right? You get fluid-driven aseismic slip events in this region. You get swarm seismicity here. I'll show one. This is another model where we reduce that healing and sealing time scale to make it shorter, and we get, in this case, periodic slow slip events at depth. Each of them gradually pushes up the locking depth by a little bit. This one I think is best shown in a movie. What's shown here, this is a space-time plot of slip velocity and time steps. This is slip velocity at linear scale, so you'll see earthquakes here. This is slip velocity at log scale, so you'll see slow slip events, permeability, upward fluid flux, and then effective normal stress, right? Changes in fluid pressure. Fluids are being fed in at a steady rate from below. That increases fluid pressure and decreases effective stress. That weakens the fault here. That causes it to slip, right? You can see the slip velocities are going close to steady state, a little bit higher at the tip of this. They're like shear fluid-driven shear cracks. Because it's slipping, the permeability is higher, and then the fluids can ascend, but they're stalled up here, right? The permeability has really dropped here due to healing and sealing, so there's not much fluid flow. The fluids are ponding there and pressurizing. And so this model produces these periodic slow slip events. You can see that they're occurring spontaneously, which tells you that a steady state in this region is unstable, and that's something that we've confirmed with linear stability analysis and also more simplified, more idealized simulations. So let me just touch briefly on that. So this is recent work by Soozawa. And so we did a much simpler setup here where we disable gravity. We're going to have a fault that's velocity either weakening or strengthening, but constant properties instead of depth-dependent properties here, driven by imposed sliding on the two sides, fluid flow again through a fault zone. We feed it in and pull it out at a constant rate here, right, that leads to this steady state fluid pressure distribution. But then we use that same permeability evolution model. In this model, we've disabled that dependence of permeability on effective stress, so that disables the possibility of what we see being these Rice et al. Solitary waves of overpressure. And this setup can, give rise to those same periodic, or in some cases not periodic, slow slip events, fluid-driven aseismic slip. It shows that steady sliding is unstable, and this example shows you that it can even happen with velocity weakening friction. So this is slip velocity here. You see these pulses propagating. They're spontaneously generated at one side and propagate in the direction of fluid flow. Here's the permeability evolving, right? It's high during slip and then heals, and then another one ruptures through. Here's the effective stress. So you see that it is, right, this high fluid pressure, low effective stress that's driving this phenomenon. And we can map out, of course, in parameter space how this occurs, right? Velocity strengthening, velocity weakening, increased fluid flux, and we see transitions between stable solutions, slow slip solutions, and seismic events. And the seismic events are really, sometimes they're nice periodic, sometimes they're more like swarm-like seismicity. So lots of fun things, I think, for us to, as a field, to figure out about fluids. So let me stop here. I am quite convinced, as I think other speakers are in this session, that fluids and pore pressure dynamics are key components of earthquake modeling. But as you've seen from the very different models and their predictions, I think we're really still sorting out what's the right way to set up these models, what processes are most important. And there's many things that I think are important to add. A lot involves getting into specific processes that are relevant at different depths, thinking about what the actual fault zone structure is at different depths. Fault normal flow, I've neglected it in these models, but it could be important in certain regions. And then a lot of these process-specific ones come down to chemistry, right? What are the dehydration reactions? There's reaction kinetics for dissolution and precipitation of silica. Some people think it's important on cycle time scales. Some people think it's only interseismic and longer time scales. And then none of us have added in temperature effects, which are super important. So lots of fun things to explore. So thank you.